Hello everyone, this is Linu. Welcome to LearnBiz. Hope you guys are doing well. In today's video, we are going to discuss crystal field theory of coordination compounds. Hope you have watched the last video about valence bond theory of coordination compounds. If not, please go and watch that video first. Okay, so you'll get complete idea about what is a coordination compound, etc. And here we are going to deal with crystal field theory. Okay, CFT, crystal field theory. First of all, we have to know what this theory consider. Okay, in this theory, ligands. Okay, ligands are considered as what? Ligands are considered as negative point charges. Okay, they are considered as negative point charges, and the bonding, we know that metal and ligands will have a bonding, right? The bonding between this ligand and the metal is purely electrostatic, because ligands are considered as negative point charges, right? So metal, we know it is already positive charge, so they will have the electrostatic force of attraction between them. So we have to consider this bonding as what? Purely electrostatic in nature. Okay, then if the ligands, like neutral ligands, we know that neutral ligands like water, ammonia, etc. So we have to take the negative end of the dipole. Okay, negative end of that dipole of that ligand is attracted towards the central positive ion. Okay, so we can consider that too as what? Purely electrostatic in nature. Okay, and in the case of free metal ion, when the metal is in free state or ion without the approach of ligands, all the d orbitals of this metal, these are the d orbitals of the metal, all the d orbitals are having same energy. That means they are degenerate. What are the different d orbitals of an metal? Like dxy, dyz, dxz, dx square minus y square, and dz square. These are the 5 d orbitals of the metal. They are having same energy in the case of free metal atom or ion. However, this degeneracy is lost on the approach of the ligands due to unsymmetrical negative field provided by the ligand. So ligand is providing an unsymmetrical negative field. Due to that, this degeneracy is lost. Okay, and the splitting takes place, and these degenerate d orbitals start splitting. Okay, and they will split into two. Okay, but we have to see that it depends on that what? It depends on the field, crystal field. Okay, so that splitting is called as what? Crystal field splitting. Okay, crystal field splitting. So first we are going to consider the crystal field splitting of octahedral complexes. Octahedral. Very simple, and we know, first of all, we should know the shapes of the d orbitals, 5 d orbitals, and we know that this is x and y. If it is dxy, it is between the axis, between this axis. Okay, as in the case of xy, if it is dx square minus y square, what is the difference? It is along this axis. Okay, along this axis are the lobes. Okay, so this is the difference, basic difference. dxy, dyz, and dxz. Okay, all are similar. Okay, all are similar here. And here dx square minus y square and dz square. So how is the shape of dz square? It is like this, dz square. It is also along the axis. Okay, that is the first thing you must know before starting the octahedral splitting. Okay, if you know this is very simple octahedral splitting. Let us consider the metal ion at the center. Ligands occupy, so it is an octahedron, right? Ligands are occupying at the corners of the octahedron. Okay, so what are to consider? Central, we have metal ion, positive charge. Okay, then we have ligands, where ligands are present at the 6 corners of octahedron, right? Corners of octahedron. Okay, so what will happen as the ligands approach? So these are the ligands. So let us consider ligands. D orbitals are here. sorry, metals d orbitals are here. When the ligands approach these metals d orbitals, what will happen? Okay, all the d orbitals have raised their energy. Okay, all will raise some amount of energy related to this. This is the free ion. Nobody is there. No ligands are approaching here. Okay, free ions, d orbitals. When the ligands approach, all of them raise to energy. Okay, and since these dxy x square minus y square and dz square, these two orbitals are sitting along the axis, right? They are sitting along the axis means ligands will have a higher repulsion here. Ligands are also present at the corners. Okay, so these ligands are approaching through this axis. So these d orbitals will suffer more repulsion. So they are raised to their energy, raised to some amount of energy. Okay, and we call them as Eg orbitals, E and small g. Okay, Eg orbitals. And the other one will have lower the energy because they are between the axis, right? So their energy is lower. That you will get, it is having T2G orbitals. T2G orbitals. Okay, that is the thing you have to understand. One is raised, that is Eg, and one is decreased energy, that is T2G. Why it is raised? Because it is along the axis, there is lot of repulsion. Okay, and why it is lowered? Because these T2Gs are between the axis, less repulsion compared to Eg orbitals. Okay, so that is a difference. And you have to understand one more thing, the difference, the energy separation between these T2G and Eg is denoted by the letter delta O. Okay, and we call it as crystal field splitting energy. Splitting energy. Crystal field splitting energy. Okay, and one more thing you have to understand, the energy of the two Eg orbitals. So these two Eg orbitals, energy of these two Eg orbitals will increase. How much it is increasing? So this is the base. How much it is increasing? It is increasing about 3 by 5 of delta O. Okay, 3 by 5 of the delta O, that is about 0.6 delta O. 0.6. And this T2G, this is T2G, I told, this is decreasing by about 2 by 5. Okay, 2 by 5 delta O, that is equal to 0.4 delta O. So basically you must know the values very clearly, then only you can calculate crystal field splitting energy. So just keep this diagram in your mind very well. So you're getting raised to energy little bit. So Eg here and decreased energy, and it is T2G here. Okay, and the difference between these is delta O. And here how much energy is raised? How much energy is raised? 0.6 delta O. And how much is decreased? 0.4 delta O. That is the thing you have to understand. Okay. And how will you calculate crystal field splitting energy? Okay, you have to calculate that. Before that, we have to study one more thing, that is, in the case of octahedral complex, when there comes D1 and D2 and D3, what will happen? If it is D1, T2G1, right? That electron will be filled in T2G. If it is D2, what will happen? It is again filled in T2G, right? And it is G3, what will happen? It is again filled in T2G3. Okay. So that means here 1, 1, 1 is filled. Okay. So this is Eg. This is T2G. This is Eg. What will happen when there comes D4? Okay. So there are two chances for D4 ion, right? That means the configuration can be become T2G4. T2G4 means it can pair. Okay, and Eg0, T2G4 and Eg0, or it can be what? That is T2G4, Eg0, or it can be what? It can be T2G3 and next to Eg level Eg1. Okay, both are possible, two cases. And what is happening here? Which case we have to consider? So here pairing takes place, right? Here D4, it becomes D2G4 like this, right? Yes, pairing takes place. Okay, when it will pair? Okay, when will it pair? That is we have to know. It will pair, this will pair, pairing takes place if that splitting, the crystal field splitting energy, that is delta O, is very greater than pairing energy. If delta O is very greater, that means what? This gap is very greater, right? This gap is very, this energy is big. So they will prefer to pair. Okay, that is the case. Okay, if that delta O is less, delta O, they can easily jump into each level, right? So they will jump and become this configuration. So two configurations are possible in the case of D4 configuration. Okay, that is the thing you have to understand. D4. Whenever we reach D4, we have to choose between two. So we have to consider delta O, that is splitting energy, as well as pairing energy. If delta O is very greater, so it will prefer to what? Pair. If delta O is less, then the fourth electron will jump to EG. That is the thing. Okay. Hope you understand. Okay. Now moving to the crystal field splitting energy calculation. We know that it is decreased by zero point 0.4, right? So 0.4, that is decreased, so you have to put a minus. How many electrons are there? You have to consider it as X. And plus increases by 0.6, right? So 0.6 times how many electrons in that Y. So you can calculate easily the crystal field splitting energy. Okay. Or you can calculate this by the equation. If you find this in terms of dq, that is very simple. Minus 4x plus 6y times dq. Okay. Okay. Now we will discuss about what? We will discuss about tetrahedral field. Okay. Octahedral field is clear. I hope you get it. Okay. Now moving to tetrahedral. It is just opposite of octahedral. Okay. Very simple. Tetrahedral. Okay. So in tetrahedral arrangement, the three d orbitals, that is dxy, dyz, and dxz. Okay. They are pointing close to the direction where ligands are approaching. Okay. So that means energy of these orbitals increases more compared to the next one. That is only difference, just a reverse of octahedral field. Okay, so I will draw that these are the 5 degenerate orbitals. They will raise their energy when the ligands start approaching, and they will split, and these are close to the ligand coming, close to the ligand's direction. Okay, ligand's approach. Okay, close. So they will raise their energy, and you will get T2G up. Okay, and what? EG below. Okay, all others are same. And this is for tetrahedral field. So the splitting between EG and T2G will become delta T. Okay, and you have to study the difference in that. How much it is raised? It is raised 0.4 delta T, and it is decreased what? Decreased about 0.6 delta T. Okay, so how will you calculate the crystal field splitting energy of tetrahedral? Right, minus 0.6 delta T plus 0.4 delta T. Okay, sorry, we have to add X and Y, right? Okay, once again. Take this delta D overall outside. How many electrons are there in EG, that is X, and this is Y. Okay, so this is called as crystal field splitting energy of tetrahedral field. This is the calculation. Just reverse, you have to understand. That is only difference because these are close to the ligand's approach, dxy, dyz, and dx. Okay, so that's all about what tetrahedral splitting. And you should know what are the factors affecting the magnitude of this crystal field splitting. Okay, factors. Basically, there are 4 factors. First one, oxidation state of the metal ion. Okay, oxidation state. If the oxidation state, that means charge, right? If the charge of the metal ion is higher, that means higher splitting will take place. Okay. So just write down higher charge. That means what? Higher splitting. Splitting will be greater. Okay. Then what is the second factor? That is geometry. Okay. And one more thing you have to study here, very important point, that is the difference between tetrahedral and octahedral split. Okay. That is also very important. Tetrahedral splitting is about how many times the tetrahedral splitting is about 4 pi 9 times octahedral split. This equation is very important because this will come in the MCQs. Okay, very important. It will give us 4 by 9, 5 by 9 by 4, like that. Different varieties they will give in the exam, and you will get confused. Okay, so delta T is equal to 4 by 9 delta O. That is the main equation. Tetrahedral splitting is small compared to what octahedral splitting. It is about 4 by 9 of delta O. Okay, and the second factor is that yeah, and second factor is this. Then third one is nature of ligand. Nature of ligand is also a factor, right? Strong ligands, when there come strong ligands like Cn minus, NH3, etc., what will happen? Large splitting will take place, large splitting. Okay. Just opposite the weak ligands, okay, which causes what? Small degree of splitting. Just opposite. I'm not writing that. Okay. And the last one is very important. Nature of the metal ion. Nature of metal ion. Metal ion. That means it depends upon which d orbitals they are. If it is 3D, yeah, 4D, yeah, 5D. Okay. So the values is like this. 3D is less than 4D is less than 5D. Okay. That is the main thing. Nature of the metal ion, metal ion, which is present in 3D, 4D, or 5D. 3D will be less compared to 4D and 5D. The splitting. Okay. Yes, these are the main factors that is affecting what? Crystal field splitting. Okay. So hope you enjoyed the video. If you find the videos helpful, so just hit the subscribe button and click the bell icon so you will never miss an update from us. Okay. If you have any suggestions or comments, you can write it in the comment box. I would like to hear from you, and any more topics you want, you feel difficult in this chapter or any other chapters, you can also comment in the comment box. Okay, then we have so many topics coming, so just wait. You have to subscribe our channel, you will get all the updates from us. Okay, yes, stay curious, keep learning, and we will discuss the remaining part of this topic in the next video. Till then, goodbye, thank you, take care, bye for now.